Welcome to Module 2. Now that we've covered the foundational principles of soil mechanics, we'll explore how to apply these concepts in actual engineering practice. In this module, we'll look at bearing capacity of soils, foundations, normal and deep, slope stability, site investigations. Let's start with the core concept that underpins all structural foundations, bearing capacity. Headphone 1. Bearing capacity of soils. Bearing capacity refers to the maximum load that a soil can carry without failure. This concept helps engineers decide how deep and wide a foundation should be. There are three types of bearing capacity. Ultimate bearing capacity is the maximum load the soil can handle before failing. Net bearing capacity accounts for the weight of the soil itself above the foundation. Allowable bearing capacity includes a safety factor and is what engineers actually use in design. Theoretical methods, like those developed by Tazagi, Meyerhoff, and Vesic, help calculate bearing capacity based on soil type, footing shape, and foundation depth. However, many field conditions require adjustments. For example, a shallow water table reduces soil strength. Wide footings distribute loads better. Inclined or eccentric loads change the stress distribution. Field tests, such as the standard penetration test and plate load test, give more accurate estimates of how a particular site will behave. Headphone 2. Foundations, normal and deep. Foundations transfer structural loads to the soil. We categorize them into small blue diamond shallow foundations, used when strong soil is close to the surface. They include spread footings, which support columns, strip footings, often used beneath walls, mat or raft foundations, which cover large areas, useful for weak soils or heavy structures. Shallow foundations are relatively easy to build and cost-effective but not suitable for all soil types. Small blue diamond deep foundations. These are used when good soil lies deep below the surface. Two common types are piles, long columns inserted deep into the ground, transferring loads by friction or by end bearing on a strong layer. Caissons, large diameter drilled shafts, often used for bridges or towers. Piles can be driven, bored, or screwed into the ground. Their capacity depends on soil friction along the sides and pressure at the bottom. Engineers use a combination of theory, field testing, and past experience to choose the most suitable foundation type. Load testing is the most reliable way to verify a pile's performance under actual loading conditions. When piles are placed in groups, their interactions can reduce their efficiency, which must be considered in design. 3. Slope stability. Natural and man-made slopes are everywhere, from road embankments to riverbanks. Slope failure is dangerous and can occur gradually or suddenly. Small blue diamond types of slope failure. Rotational failures, which are curved and often occur in clay soils. Translational failures, where the slide occurs along a flat surface. Toppling or rock falls, which happen in hilly or mountainous terrain. Small blue diamond factors affecting stability. Soil type and layering. Presence of water. Slope height and steepness. External loads like traffic or construction. Engineers assess slope stability using a factor of safety, which compares the resisting forces to the driving forces. If the factor is less than 1, the slope is unsafe. Several analytical methods exist, some basic, others complex, but all aim to understand the conditions under which a slope might fail. Small blue diamond slope stabilization techniques. When a slope is found to be unstable, we can use various stabilization methods. Improving drainage, to reduce water pressure. Flattening the slope, to decrease the driving force. Reinforcement, using materials like geotextiles or soil nails. Constructing retaining walls to physically restrain the soil. Planting vegetation, which helps prevent erosion and increases slope stability. Headphone 4. Site investigations. Before starting construction, engineers must understand the ground beneath the project. This is the purpose of site investigation. Small blue diamond goals of site investigation. Understand soil and rock properties. Determine groundwater conditions. Identify potential hazards. Provide data for design. Small blue diamond phases of investigation. Desk study, Review maps, area photos, and previous reports. Reconnaissance, visit the site to observe physical conditions. Subsurface exploration, use boreholes and test pits to collect samples. Small blue diamond methods and tests. Boring methods include auger, rotary, and percussion drilling. Soil sampling provides material for lab testing. Samples can be disturbed for classification or undisturbed for strength and compressibility tests. In situ tests such as standard penetration test (SPT), cone penetration test (CPT), vein shear test, permeability and pressure meter test. All this information is compiled into a geotechnical report, which includes soil profiles, groundwater data, and recommendations for foundations and earthworks. Headphone conclusion of Module 2. And that's a wrap for Module 2. Let's briefly summarize. Bearing capacity tells us how much load the soil can handle. Shallow and deep foundations help transfer structural loads to the ground safely. Slope stability is critical for preventing landslides and ensuring long-term safety. Site investigations give engineers the essential data they need for smart, safe design. Headphone final course summary. Over the 2 modules, we've explored the science and engineering of soil behavior and design. From understanding stress and consolidation to designing foundations and preventing slope failures, geotechnical engineering is the hidden strength behind every successful structure.